So in this scenario, we've got a circuit, and we've got charges flowing through the circuit, and the charges also can flow through the rod because it is a conductive rod. But that rod is not fixed to the wires, or the circuit itself, so it is free to move up and down along those wires. And it shows you that the current is going up, or we can call it into the page. So first we need to find the direction and magnitude of the net force on the rod. Using the right-hand rule, the current is going to go in while the magnetic field goes up. So I use the right-hand rule where my thumb goes into the page, my fingers represent the magnetic field pointing up, and my palm is then pointing outward to the right. And so the direction of magnitude of the magnetic force is to the right. It is going to push it in that direction, so FB. Determine the speed of the rod as a function of time. In this scenario, we want to find an equation that uses acceleration, because acceleration can be represented as a function of time. So we've got the magnetic force. I'm going to do B down here. That is equal to, given the variables, it's going to be this equation, ILB, and we know that force is equal to MA. Now, we can make the assumption, because we're trying to find the speed of the rod. We can make the assumption that the rod is starting from rest, and so acceleration is the change in velocity over time, which is V final minus V initial, but V initial is just going to be 0. So it's really just V over T. So now we can plug in and solve for velocity. ILB is equal to mv over t. This is my acceleration equation. And therefore, V is equal to ILB times time divided by mass. And that would be your final answer for B. For C, we want to find the distance the rod must move from rest to reach speed V. Originally, I wanted to plug in this equation for speed into my solution, but they just want you to leave it in terms of V. So in this scenario, to find distance, we're going to use a kinematic equation. Our initial position is 0. Our initial velocity is equal to 0, and our V, we're going to call it this V, is going to just stay V, but it's some function in terms of time. And then we're solving for delta x, or rather x final. Okay, so the common equation we've been using is V final squared equals V initial squared plus 2a x, or delta x, but x not a 0. Initial is 0. Our final velocity is going to be this function, but as I stated, the answer key just leaves it as V. And so V squared is equal to 2ax, and therefore x is equal to V squared over 2a. Now, a is not given as a variable that we can use, although velocity is going to be a variable they want you to keep it in. And so to find a substitute for acceleration, we are going to take the acceleration from part B and solve for A, which gives me ILB over mass. And when I plug that into this equation, the acceleration will, we can just multiply it by the reciprocal, and I get V squared A v squared m over ILB times this whole thing times 2. Okay, so for part D, we've got a frictional force that is opposing the magnetic force pulling it to the right. So what we want to solve for is the new distance, so we're solving for x, that the rod must move in order to attain the same speed found in C. So we want the V final to be whatever V final we got here. And so if I solve, my V final would be 2ax, and we don't know this x, or it's a square root of 2x. We don't know this x, but that's what we're trying to isolate. So we're going to now take the sum of the forces. Force magnetic minus force of friction equals MA. Because we want the same velocity, our acceleration is going to be V, and I don't even need to call it V final, but V squared all over 2x. That's what I'm going to substitute into the equation. So I've got ILB minus mu times the normal force. The normal force here is mg. That's equal to m times our acceleration equation, v squared over 2x. And then we solve for x here. So let me start by multiplying 2x to both sides and dividing the ILB minus mu mg to the other side, and then I'm going to divide the 2. So x is equal to mv squared over 2 times ILB minus mu mg, and I think it just leaves it in that form.